In this lecture, we will discuss the magnetic dipole placed in a magnetic field. But before going into the details of this topic, let us first recall the topic 28.7 of chapter 28, which was about a dipole placed in an electric field. If you recall, whenever a dipole is placed in an electric field, this combination of positive and negative charges, which are equal and opposite charges, is called the dipole, and the dipole moment P is directed from the negative charge towards the positive charge. This is the dipole moment vector P, and it is making an angle theta with the electric field E. This is our angle theta, which is the angle between E and P. The effect of this electric field was to align this P with E. As you can see over here, there are two equal and opposite forces acting on these two charges, which is giving rise to a couple, and due to this couple, the dipole, the vector P, will rotate, and it will rotate until and unless it is aligned with P. So the torque acting on the dipole placed in an electric field tends to rotate it, and it tends to align it with the electric field E. The value of that torque acting on the dipole moment vector P placed in an electric field E was given by P cross E, or it was equal to P E into sine of theta, where theta is the angle between P and E. Similarly, the potential energy which is stored in this dipole when it is rotated by the torque through an angle theta in the electric field E was given by minus P E cos of theta, and this P E cos of theta can be written as P dot E. Here it would be minimum when P and E are parallel to each other. This is just to recall about the electric dipole placed in an electric field E. So once again, the torque acting on this electric dipole was P E sine of theta, and the potential energy stored here was U was equal to minus P dot E. Now let's come to the topic of our today's discussion, which is about the magnetic dipole moment. The magnetic dipole moment is a vector which can be thought of as a current loop carrying a current I and having an area A. So the direction of that magnetic dipole moment will again be given by the right hand rule. If we stretch our thumb and curl the fingers of our right hand in the direction of the current, then the stretched thumb will give us the direction of the magnetic dipole moment for that current loop. And its magnitude will be equal to the current I carried by the loop and the area A of the loop. So mu equal to IA represents the magnetic dipole moment, and its direction will be along the outward drawn normal to this area, which again is determined by the right hand rule. So mu is a vector having a direction along the outward drawn normal to the plane of the area of the loop, and its magnitude is equal to the product of the current I and the area A of the loop, of the current loop. The torque on this current loop can be written as T is equal to mu cross B in analogy with the torque on the electric dipole placed in an electric field, which was equal to P cross E. So here P will be replaced by mu and E is replaced by B. So this cross product gives us the torque acting on the current loop. Now this mu is equal to the product of I and A. So this can be written as this would be equal to mu is I times A into the magnetic field B into sine of theta, Now let me write theta as this equation is the same as the torque acting on the rectangular loop placed in a magnetic field. Just go back to your last topic and confirm that the torque acting on the rectangular current loop was also the same, that is IAB sine of theta, where theta was the angle between the normal to the loop and the magnetic field B in which that current loop was placed. The only difference is that that loop was rectangular in shape and here we are having a circular loop. So this is a torque acting on any current loop of any shape carrying the current I, having the area A placed in the magnetic field B, and it's the normal to the area A makes an angle theta with the magnetic field B. So this theta is the angle between A and B, the area of the loop and the magnetic field B. But remember that area has a direction along the outward drawn normal to the plane of the area. So this is the theta between the normal to the plane of the loop and the magnetic field B in which it is placed. So torque acting on any current loop will be equal to mu cross B, and its action would be to bring mu into alignment with B. It will become 0 when A and B are aligned with each other. That is the normal to the loop, the normal to the area or to the loop, and the magnetic field B, when they are aligned with each other or when they become parallel to each other, the torque ends, or the torque stops acting